definition there. So let's look at it. So looking at the repeated ones. So if I had this thing, the nth power times an eigenvector must be 0, but the n minus 1 power of it is not 0. That's where the problem comes in. So first one, no sweat. All the others, problem. All right, so here's the general structure of what this thing is. So the nth eigenvector, find it as v. Right? Then I can find the n minus 1, that's the repeated one. So I have 3 repeated eigenvalues. I'll have 3 eigenvectors I need to worry about here. First one will be the eigenvector. Second one is I minus lambda n times the first eigenvector, which will be equal to my original structure here. A minus lambda I times the eigenvectors. The next one is this squared times the original eigenvector. So if you see a pattern, originally I have an eigenvector, a minus lambda I times that eigenvector, a minus lambda I squared times your first eigenvector. So it's always this first eigenvector always there. Or kind of writing it a little bit easier form, a times the first repeated eigenvector problem equal to lambda v. The second time, it's this first one times lambda v1, third one v2 times lambda v3. Right, that's a pattern that shows up on these things. Where lambda is that repeated eigenvalue. Put it in matrix form, you get this. Okay. So can't call that eigenvectors so much, or eigenvalues. But if I have, in this case, 4 of the same eigenvalues, same eigenvalue, then I've got to put a 1 up there, and so forth. That pattern always repeats down here. It's called the Jordan block form. Ever seen the Jordan form before? This is the most general form for eigenvalues, eigenvector problem. Right? It is not diagonal, right? But it is a solvable solution for it. Okay. You can do this MATLAB. I don't know what version of the book things you have. There used to be a command called Jordan. Create these things. Newer versions, at least version 5 and higher, I've seen, you have to go into this called guide block. And I think the newer one changed to be a versions. We're doing a measure for it. But it's a little awkward MATLAB to create these things. I think they got better than later versions of it. But right, look on their help file on Jordan platform, so that's what you can find to help whatever version of MATLAB you have to have. But you can create it. Okay. All right. So let's remember how to find eigenvalues. Let's keep it simple. I have this A matrix, right? And you know that lambda I minus A, or A minus lambda I, doesn't matter. I can solve for it, right? And the determinant will be, for this case, simply lambda minus 2, lambda plus 1, and lambda. Right? So just went back and found the determinant of this matrix. Right? Everybody can get the determinant of 3 by 3, right? You get the inverse of the 3 by 3, right? Without MATLAB. Expect you to be able to do that for a test. Okay, so I got the determinant. So my eigenvalues are what? Plus 2 minus 1 is 0. Okay. The roots of the characters. Right? So for each of these eigenvalues, this must be the case. The trick is what your matrix is. All right, so we can go through one by one. So I'll start with lambda equals 2. That first eigenvalue goes to there. And put in that lambda equals 2. Okay, so A minus 2 times the identity measure for Q must be that. It must be equal to 0. So how do I solve for Q? Well, that's really what I've written here is what? Set of linear equations, all equal to 0. So minus 2 times Q1 equals 0. Q1 minus Q2 plus 2Q3 must be 0. And then the last one's Q2 minus Q3 must be 0. So all three of those have to hold. But what happens? Yeah, they're not independent. Yeah, they'll be 0, but I have an infinite number of values of Q that will make those get 0. Because I do not have a set, independent set of equations here. So what do you do? I don't get a unique solution here, so when I don't have a unique solution, what do? Pick a value. No. One possibility. So, pick one. Let's say Q2 is equal to 1. Pick that value. Then I can solve for Q1 and Q3, and then get that. Then you do it for lambda equals minus 1. Exactly the same exact process. Well, here's the A minus this I. Yeah. Same thing, so get linear equations, same problem, Q1, 0, okay. In fact, this one's up to Q1, 0, and I can solve basically a set here, 0, minus 1, minus 2, 1. And then do it for the last one. Oh, they're all zeros in this case. So my Q's 2, 1, minus 1. Okay. So my eigenvector matrix is now, here's the first one, 0, 1, 0, minus 2, 1, 2, 1, minus 1. Okay. And the next thing to do is check to make sure you did it right. So for that eigenvector, let's calculate Q inverse AQ, and I got that. And what do I have on the diagonal? So what's the diagonal here? It's the eigenvalues. Let's check. Okay, so this ring bells to you. And for those vibration special, we do exactly the same thing. So for this class, the meaning of the eigenvalues is what? What's the meaning of it? Do they have any meaning? The eigenvalues are what? The roots of what? Kirchhoff's equation in the system. Yeah. And what do the roots of the Kirchhoff's equation tell us? Those they had 52, 6200.
Dynamics.
What's that?
Dynamics of the system.
Dynamics of the system. In fact, for this system, what can you tell me? I have 2 minus 1, 0. It's unstable. I have a hole in the right hand corner. And the 0 means what?
You have.
Yeah, that's actually a pure integrator. I have an unstable kind of right hand plane pole. I right hand always negative things. So what we'll do in this class, we'll be able to choose the whole set of those things under control. So that's basically this. All right. Questions on that? Any questions on similarity transformations? The other thing we'll use in this class is called the Cayley-Hamilton theorem.
Quick question.
Yeah, oh, yeah.
So is the purpose of doing this then to find those eigenvalues and then to find the characteristics of the system? Is that kind of the purpose?
Yeah, what's the purpose of diagonalizing? Well, one thing, I want to be able to know what the roots of the characteristic equation are. Because that's going to tell me, that's what I'm going to design for. It says, I want my roots of the characteristic equation to be here, here, and here. Might end up with this thing as this, well, it's an unstable system. So I got to do something to make the system stable. Right? Diagonalizing is one way of doing it, although we usually don't have to diagonalize to get characteristic equation. All I have to do is find the determinant of SR minus A. Right? Or minus SR, whichever you like. But the important thing is I want to know what the roots of characteristic equation are. And for most systems, we have nice numbers. Yeah, that will do it for us. Find determinant measures, whatever. It's usually pretty easy. Right? Okay. Any other questions? Yeah.
So to get the Q matrix, you just took each.
Yeah, I found a set of Q matrices.
Okay.
Well, in fact, it was by choosing a value. You know, it's like, make one of one subtract it. What's the other way of doing it? Maybe a more common way you might see in MATLAB should do this too. What's the other way? Out of this infinite number of solutions for the non-independent set of equations, well, if I have three equations, but they're not independent, what's another way of solving? Create a fourth equation. What's that fourth equation? Typically. So here's one where I chose this value, found the rest, chose that one, found the rest, so forth. That's the way of doing it. What's another way? I could create a fourth equation. What would be that fourth equation? It could be anything I want, but what's a very convenient one to use? Right? When you do eigenvalue, eigenvector problem in MATLAB, what comes out in your eigenvectors? What, tell me anything about that form. You've done that, seen what the structure is. Could you tell me what the length of that vector is? First one, 0, 1, 1. What's the length of that vector?
1.
Where is it? Square root of 2. Okay. And for the second one, what's the length of this vector? 5. I think square root of 5. Right. For right. How can I make those lengths all one? Basically, that's the fourth equation I can throw in. Make the length of all my eigenvectors 1. And that's what MATLAB does. That's what typically is done. And anyone taken the statistics class this year with Dr. Merriweather? I should be. You come in the same problem with statistics. It's called principal components. And it's exactly the same thing. You're looking at eigenvectors, and again, all the lengths will be set to 1. So that's probably the most common way these things are set up. Create a fourth equation, make the eigenvectors all the length of 1. That means that the determinant of Q is what? 1. All length of 1 determines going to be 1. Okay. Right. So I'm going to get to another theorem, which you may have never heard of, called the Cayley-Hamilton theorem. And we use this in this class here. Essentially, if I take the determinant of lambda I minus A, it's essentially lambda to the nth power plus some matrix alpha 1, lambda n minus 1, so forth, all the way up to A span. Alpha span, 3 letters. And that's the same thing as really what's called Bell lambda, which is the diagonal matrix of lambda. Right? Well, the determinant is characteristic of A. And since A and lambda are similar, you have to have the same characteristic equations. That says, instead of saying lambda to the n plus alpha 1 and lambda to the n minus 1, I can put in A, minus 1, A, n minus 1, so forth, all the way up to alpha x of n times r. So instead of putting lambdas, I can put in the A matrix. Right? Does that feel good for you? I can do that? And it's because they're similar. That lambda I and A are similar, therefore, if the characteristic equation I can write in terms of all these powers of lambdas, I can do the same thing in powers of A. Basically, what it says is that a matrix satisfies its own characteristic equation. Of course, kind of sense here. This form we'll use to make some of our calculations a lot easier. I want to introduce now, we're going to come back to this, but we're going to use this structure. Okay? And our alphas are what? What are the alphas? Well, if this is the characteristic equation, what are the alphas? What's the coefficients of the characteristic equation? Yeah. So I have this in terms of coefficients of the characteristic equation. Maybe I can solve this. All right. Anyone ever seen Taylor Hamilton there before? Probably not. Hopefully we'll use it in the All right. The last bit of linear algebra I want to talk about are norms. They're basically lengths of vectors, but there are a lot of different ways you can kind of figure out lengths of vectors. Now we'll look at some boxes. And these double bars mean norm on it. And the norm is always greater than 0 for every x whether positive, negative, whatever. It's always going to be greater than, always going to be positive values. And 0, if and only if, it's IFF in the proper mathematical terminology, if the x vectors are all the way that can never be 0. Also, if I look at the norm of some constant times the x matrix, so I look at the absolute value of that, since this is a constant, just absolute value times the norm of x for any real value of alpha. Right? And then the third one, this is one often people kind of get confused, but it kind of makes sense if you think about it. If I have two matrices, A, or two vectors, A are x1 and x2, and I add them, find the norm, that must be less than or equal to the norm of x1 plus the norm of x2. Why would that be less than? Yeah.
I mean, you think of it as like a triangle sort of thing. If you add any two sides of the triangle, the length is going to be greater than the third
Yes,
side.
exactly. That's a good analogy for it. Very good analogy. Same idea. Right? All right. Now, there's a lot more than the types of norms you might think of. In fact, how do you find a normal for a matrix typically? You guys do it. It's usually what the just x squares type of thing. Right? Let's see, length, yeah, length. But there's a lot of other norms. There's absolute value. I do the sum of the absolute value of every x vector. Add them all up. Right? It's called a one norm. The two norms are what you probably typically are used to, the Euclidean norm. Or take every coefficient of my vector, x, square it, add them up, and you take the square root of them. Now, that's kind of the Pythagorean theorem length of a vector type of thing.